Great to be here. Welcome, everybody, to the Aspen Center for Physics Free Physics Lecture, sponsored by the Nick and Maggie DeWolf Foundation, which, as Emily said, has sponsored lectures here since 1985. So it's been 40 years. Amazing. Their generosity and the generosity of every lecturer, like Professor Berta-Thompson, makes it possible to share the new research that's moving the frontiers of science forward. And it's our way of thanking the Aspen community for supporting the center to host these lectures. And so I'm very honored to be here. I'm here as part of one conference, as Emily said, which is on the atmospheric characterization of rocky to giant exoplanets and thermal emission, JWST. So that might sound like a garbled phrase to you, but Professor Berta Thompson will explain it in clear detail in this presentation. And people here for this meeting are interdisciplinary scientists encompassing astrophysicists, geophysicists, and everything in between. And in this week, we're focused on three main topics. One, searching for atmospheres on rocky planets. Two, discovering the nature of planets between Earth and Neptune in size. And three, understanding the formation and evolution of gaseous planets, as you see on Professor Berta Thompson's first slide. And despite long days, we leave refreshed with new ideas. Aspen is a great place for inspiration in winter and summer, and the Aspen Center for Physics is an idyllic place to come together and chat about science. I feel very lucky to be here tonight, and I also feel fortunate to have as our speaker tonight Professor Zach Berta Thompson, who is coming to us from the Department of Astrophysical and Planetary Sciences, the University of Colorado at Boulder. So he only had to drive here, which is quite nice, and so I think it's very fitting that he's our guest lecturer tonight. Professor Berta Thompson received his AB in Astrophysical Sciences at Princeton and his PhD in Astronomy at Harvard. Then, after a postdoctoral stint at MIT, he's been a professor at UC Boulder since 2016. And he's won many awards, most notably a 2020 NSF Career Award. And he was also previously a TEDx Boulder speaker in 2019. And Professor Berta Thompson's research focused on using telescopes to both discover exoplanets as well as to characterize atmospheres. And he is very closely involved with myriad projects, including the MIRth project to discover exoplanets, the TESS project to characterize planets and discover them, and optical, also the JWST Transiting Exoplanet Community Early Release Science Program, as well as many other JWST programs. So I look forward to learning from him over the next hour. And let's please welcome Professor Berta Thompson to the stage.
Hello, hi everyone. Nice to see all of you. And so today, my talk is titled "The Glow of Distant Worlds." This is me trying to distill the science that we've been doing at this conference this week down into kind of the methods and the how of we're doing. There's a lot of like cool scientific results that would take me hours and hours and hours and hours to explain. And so I'm not going to go through all of those in detail. Like you will see them appearing in news stories at various times. And what I want to do today is try to give you a little bit of the kind of like a little bit of a sense of methods that we're using to do this so that when you read those stories, you get a sense of where does this come from? What's the evidence? So the image that we're looking at right now is Jupiter. This is Jupiter in infrared light. Looks probably not how you're used to seeing Jupiter. This is an image that was taken with the Gemini 8-meter telescope. This is one of the kind of flagship telescopes in the NSF Noir lab. So the telescope that took this image is the collective effort of thousands of people working for decades to build those telescopes, to take care of them, to do science with them, and a broad scientific community that advocated for them. So this is what Jupiter looks like if you have amazing infrared. You might be more familiar with a Jupiter that looks like this. This is Jupiter in reflected light, reflected visible light. So this is like if you got up close to Jupiter and looked at it, this is approximately what it would look like. This is an image that was taken with the Hubble Space Telescope. So again, this is the collective effort of decades of work by thousands of people who care deeply about astronomy to build this really beautiful space telescope and launch it in the early 90s and to care for it over the years to be able to take images like these. So that reflected light image is like to connect that to what you can actually see from here on Earth. If you go out tonight and it's clear, you could see a few bright things in the sky. Some of the brightest things that you will see here will be the moon, pretty obviously. But then you'll see Jupiter and Mars as two planets in our own solar system orbiting around our sun. We're seeing light that has come from the sun bounced off of those planets and then comes to your eye. Every other point of light, so Sirius will be the brightest other star that you see in the sky. Even Orion here, every other star is another sun that is located light years or parsecs away. Sorry, light years or hundreds of light years or thousands of light years away. So far away that it takes light thousands of years. And each one of those stars might have its own planets, right? Like if those stars are suns like our own, it's very natural to think that they might have planets like our own orbiting around them. And actually, they might be different, and we might not know what they are exactly in the first place. But we should try to look for them and try to study them. So this question of what planets are there orbiting other stars is one that people have been curious about for years. But since about the mid 90s, we've actually been making a lot of progress in finding planets for other stars. The challenge that we're facing is fundamentally the exoplanets are really hard to see. So I have an imaginary little sun right here. I'm going to turn this around and shine it at you. It's going to be bright. Sorry. You. All right. So if this is our super duper bright star, and like this light bulb is about 5 centimeters. If I wanted to have Earth to scale relative to this, I would need to take a little blob of Play-Doh that is, I'm going to go for about a half a millimeter. I think I made it a little bit too big. Sorry. But a half millimeter blob of Play-Doh is the appropriate size of Earth relative to the sun. And in terms of like where this should be located, about over here. And so the challenge of looking at some other star and seeing the light that comes from that star bounces off of that planet and then travels to you is kind of the challenge that you're facing right now of there's a bright light there, there's a faint little planet right here. How many people can actually see a planet in my hand? All right, several people in the front row can see that there is something there. But then for the scale of the distance to other stars, it would be like trying to do that if we were across the country. Like if we were in Boston, pointing the telescope back here at Aspen, pointing that star, and then trying to see this little planet sitting next to it. Very, very hard thing to do. And astronomers are working on telescopes right now that would be able to do that. Probably a few more decades of work, but we're heading in that direction. But in the meantime, let's turn this around so you can see a thing. Great. So I'll let my little atmosphere keep going. In the meantime, let's play a little bit more to our strength. So astronomers have gotten really good at measuring the brightness of stars. So for over 100 years, astronomers have been making very, very precise measurements of how bright a star is, and even like watching as that star changes over time to see it get a little bit brighter and a little bit fainter. The image that I'm showing right here is of the Harvard computers. So these were women astronomers who worked at the Harvard College Observatory in the early 20th century, a little bit before. And they were experts of the time at precise photometry, measuring the brightness of stars very, very carefully. One of the more famous of these astronomers is Henrietta Swan Leavitt. He discovered these pulsating stars and figured out a relationship that fundamentally helped show that the universe is expanding. Like we know that there was a Big Bang because of the work that she did, being through thousands of photographic plates to look for these little pulsating. And so the method of doing astronomy at that time was very different from now. This is a photographic plate of a galaxy with lots of other little stars here. All of the little annotations on here are handwritten with ink by one of these computers as they went through and identified a star and cataloged its brightness and measured something about it. And to figure out exactly how precise that a star might be, they had a little reference system. It was a tool that they called a fly spanker, which was just like just a little glass plate that had some little dots on there that this is a reference star of a particular brightness. You compare the brightness of a star into that. So using this methodology, and presumably a lot of patience, in the 1920s, these astronomers could get to a photometric precision, ability to measure the brightness of a star, of about 1%, so 10 to the minus So 1 part in 100 see variations in the brightness of the star. You could see there are all sorts of variable stars that they could detect using this. Now, in the 2020s, at a conference about the James Webb Space Telescope, we've been talking a lot about photometric precision that is more on the level of 10 to the minus 5. So that's 0.001%, 1 part in 100,000 variations in the brightness of a star. So the technology has improved, and thankfully we're using, like, we can do things digitally now. We don't have to go in by hand. But fundamentally, we're building on the legacy that they built. And this is an image that was kind of taken about 30 years after the previous one. This is a community of scientists who worked together well for decades on a big, ambitious project. And reading about the history of this time, there was like they built a really beautiful, supportive community for each other at the Harvard College Observatory at a time when it was like I think it was hard to be a woman in science, right? This was like they couldn't vote for most of the time that they were working here, but they could contribute to this really foundational work that underlays all of modern. Okay, thanks to them, we can precisely measure the brightness of a star. What that means is we can find planets. But even if a planet around a star is so far away that we can't take a picture of it, meaning that we could imagine anything that it might look like. I like to imagine a star as a ball of yarn, planet as a little button passing in front of it. If you have a planet that happens to be passing in front of its star, if you measure the brightness of that star very carefully as a function of time, you'll see the star by itself, and then you'll see a little dip as the planet passes in front of the star, and then the star by itself again. And so that level will drop back up. To show you what this looks like with real data, this is data from the NASA TESS telescope. TESS, it's 4 telescopes, the Transiting Exoplanet Survey Satellite. This is HD 209458b. This is the first transiting exoplanet that was discovered, but this is real data that was taken a few years ago. And watching the brightness of the star as a function of time, and every 3.5 days, you see a little dip in brightness of the star as this planet passes in front of it, blocking about 1% of that star's light. We're really zoomed in here, and the precision on here is much better than that we can be able to see this 1% dip. And that dip tells you directly how big the planet is. Right? Like a bigger planet is going to block a larger fraction of its star's light. And so by measuring this dip and the period and a few other properties in here, we can figure out how big a planet is, how far away it is from a star. We can piece together the basic story of a planet. And for planets like these ones, where they happen to be lined up so that their planet passes in front of their star, it turns out that we can directly observe both the planet size, but also using various other methods, the details of the orbit of the planet, whether how far away it is from its star, whether it's centric. We can measure the masses of those planets, like how many kilograms of stuff make up that planet, the mass and the size. You can get density, and importantly, we can study the atmospheres of those planets as well. And this is so cool because every time we find a planet around another star, this is like another solar system that we get to study. This is another laboratory for how planetary physics works. And we get to dive into detail and figure out how planets work in an environment that might be very different from our own. So with these, with that basic tool of, okay, we can find these transiting planets, I want to introduce you to the planets. You're probably familiar with the 8 planets here: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Be a planet if you wanted to. But what I'm going to do is I'm going to get rid of all of the terabytes of beautiful data that we have on each of these planets individually, and I'm going to turn them just into basically points, like a few numbers to characterize a planet. So in the solar system, I could make a plot that looks like this. So I have the planet mass on the x-axis, planet radius on the y-axis. So how much stuff is in a planet? How big is that planet? And these are logarithmic axes. So as you go, this goes from like 0.1 Earth masses to 1 Earth mass. That's the mass of the Earth. Earth masses, 100 Earth masses, 1,000 Earth masses. And on here, you can see that Mercury, Mars, Earth, and Venus all kind of line up on a little curve that I've drawn here. This is a model for if you take a ball of rock and iron and make it bigger and bigger and bigger, or add more rock and iron to it, how big should that be? So we can describe mass and radius of the 4 inner planets in the solar system with just a ball of rock and iron. Then once you go to Uranus and Neptune, especially up to Saturn and Jupiter, they're much bigger than if you had something that was a ball of rock. they need to have a much thicker envelope of gas around there because it puffs up their size and it makes them really, really big. And so just by looking at this plot, we know that Saturn and Jupiter have to, well, and with some detailed modeling, you can say that Jupiter and Saturn have to have very thick hydrogen helium envelopes. They are mostly gas with a little bit of maybe something like rocky material. I'm going to add the exoplanets onto this population so you can see what else is out there. We'll do that first of all. Hopefully, I heard like one ooh. Yes, there are a lot of planets out there. We've discovered thousands of transiting planets and done very careful work to be able to measure the masses and radii of those planets. And so each of these little point has error bars on it because these come from measurements. So each little crosshair on here is the work of an astronomer who carefully gathered observations, analyzed those observations. Some of these were PhD students. These were scientists who put a lot of effort into figuring out the basic properties of these planets. And the trends are kind of cool that we see like for things that are similar to Earth and Venus, but still follow this kind of rock iron curve. But once you get to about, I don't know, 10-ish Earth masses, you start getting bigger and bigger planets. You need to have some kind of gaseous envelope around them. You need to have hydrogen, helium, maybe a thick layer of water, ice, or various other molecules. And so you have, and there's a huge, especially around like Uranus and Neptune, there's a huge variation that you can have a thing that is almost basically a ball of rock up to a thing that is almost the size of Jupiter because it is so inflated with very heat. And so I'm going to add another panel onto this plot. This is, I know I'm building up a complicated plot here, but we'll spend time on it. We still have planet radius, planet mass. And so the y-axis here is still planet radius. So we have big planets up here, little planets down here. And then I've added an axis here that is how much energy does a planet receive from its star? So over here, I put in closer in planets. So this is you're really close to your star. Mercury is the closest to our sun in our solar system. Neptune is way far out. And so this is how much energy do you receive from your star? Meaning effectively what temperature are you? Planets that are over here are going to be like thousands of Kelvin in temperature. Planets that are out here might be 70 Kelvin. Get really, really hot things close in, really, really cold things farther out. And so in here, there's also a band that I've drawn on here, which is a range that astronomers sometimes talk about and debate about and say we shouldn't be talking about because it's complicated and we don't know what it actually requires to have life on a planet. The one thing we do think we know about life on planets is that life probably wants liquid water. And so this is a range of distances away from your star in which it's possible for you to have liquid water at your surface. If you're closer into this, you receive more energy, then all of your water will be, your oceans will boil away. You lose all of your water out of the top of your atmosphere. If you are farther out than this, all of the water on your surface would be frozen solid in the ice. Only in a very narrow range here of sort of around Earth and Mars, we think it's possible to have liquid water at the surface of your planet and therefore potentially life. We have not discovered life on Mars. We do not think Mars is particularly habitable right now. But if Mars were a much larger planet, maybe that we're able to hang on to more of an atmosphere and have a little bit more of a greenhouse warming effect, then it's possible that Mars could have been another habitable planet in our solar system. Right now, the only one in our actual solar system that we know life can thrive on. Yep. So if I add the exoplanets onto here, these are the transiting ones, the ones that pass mostly transiting ones that pass very close in front of their stars. You see a lot of hot planets. There aren't tons of transiting planets out by Uranus and Neptune. And not because those planets don't exist, it's just they're really hard to find. You would have to wait like 100 years for one of them to transit. There are lots of biases against detecting really, really, really distant planets. So we tend to find planets that are closer in and a lot hotter. Populations you can see in here are things that are the size of Jupiter and really, really hot. The hotter you are, the bigger you are. So you're seeing some of these planets getting kind of inflated by the extra energy they're receiving from the stars. You have lots of rocky planets down here. There's a cloud of things here that are like hot Uranus and Neptune type objects that we have no idea how these work. They're weird, like there's like big questions about what those planets are like. But we know that there are lots of them out there. And if you look closely, there's a little bit of a gap here that we attribute planets being below this probably being rocky, and these ones probably hanging onto a thick envelope of gas. There's still a lot to figure out. I'm going to add one more panel to this. Bear with me, which is for planets. We can also just plot what is the size of the star that a planet orbits. And so the solar system, this is a pretty boring plot. All of the stars orbiting the sun orbit a star that has one solar radius. However, if I add exoplanets onto here, we see planets that orbit stars down to 1/10 the size of the sun, up to even more than twice the size of the sun. There's a huge range of different stars that planets orbit around. Um, I'm happy to take a baby too. We can try it. Um, yeah. Um, okay, so this is the population of planets that we have to work with. It would be lovely if we could learn more about how they work, right? If we knew more than just here's the mass and radius and basic properties of how it is. And so the next question that I have when I look at this big population of planets that exist out there is how do we observe the atmosphere? Like an atmosphere is what makes a place feel like a place, right? Like this is like I, I live in Lyons in Colorado, so we have the Rocky Mountain Botanic Gardens there. It's this beautiful community gardens where you can go walk amongst the native plants, and you can on a rainy day, you can feel water dripping down on you. You can take a big breath of air, breathe in lots of oxygen and nitrogen, and a little bit of humidity from that. I know that's rare in Colorado, but we get it. And you can see all of the stuff that is growing, photosynthesizing out of building life out of that atmosphere. Here on Earth, atmosphere is what makes Earth feel like Earth. If we had no atmosphere, it would be the moon, and that would be great. Be fine, but not nearly as fun as our actual. And so here on Earth, the way that we study our atmosphere is we go outside. You could even study it inside. It's pretty easy. Even in the solar system, we can go to atmospheres. This is a horribly complicated, a horribly complicated animation that you don't need to get too much out of. But this was the Huygens probe from the Cassini-Huygens mission. This was a collaboration between NASA and ESA, the European Space Agency. When I was in college, sent a lander down into the atmosphere of Titan, one of the moons of Saturn, and made measurements along the way. So all of these little things here whirring around are measurements that were made directly in situ in the atmosphere of Titan as this little lander was riding down in a parachute, taking a few hours coming down to land. So in the solar system, with incredible effort, we can send satellites to places and make in situ measurements that tell us the details of that atmosphere. Or when we go to exoplanets, don't go to exoplanets. When we when we want to study exoplanets, we definitely can't go there. You will never visit another star. You have to observe them remotely. So the only tool that we have to study exoplanets is light. So I want to take a minute now. I'm going to introduce you to my Astro 1030 Astro 101 version of what we need to know about light. So first of all, light is power, right? I just turned on this projector. It is pulling some number of watts out of the electrical outlet here, producing some luminosity, some power in there that this light that is being projected at me on here. So I can measure the total power that is being output by this watts. As I see it hitting this projector screen here, I might say, well, okay, within any particular patch here, there's a certain amount of power that is hitting that. And so a unit that we often talk about in astronomy is lux. That is a power, a light flux of how much power do we have per unit area. So I might talk about that as this many watts per meter squared. Here I'm probably getting, I don't know, about 100 watts per meter squared, something like that, a little bit less. I don't know exactly the numbers. But this is energy that is being produced and being transmitted through space. Just to say a cool thing, fundamentally, all of this energy is coming from the sun, right? That there's nuclear fusion that is happening at the core of the sun, producing energy at the sun, and we don't have to physically go there and charge up our batteries and bring them back. the light radiates from the sun and carries that energy to us here on Earth that we could use to start a solar panel or up a wind that turns a wind turbine, or grow into a plant that a dinosaur eats and then turns into fossil fuels that we use to power our power plant. Fundamentally, like most of the power that we have on Earth is coming from the sun or from stars. Okay, so this is so like light is power. It is also, but it's not all just one. Um, uh, it's not all just one wavelength. Um, this is you may have heard that light is a wave or is waves. Um, I don't like. There's lots of funny quantum mechanics we could talk about of what light looks like, but I like to think about light as kind of an ocean, right? The energy that is hitting me right now is kind of like the roar of ocean waves that I'm feeling. Right? An ocean isn't just one wave. It's not just a perfect like water is going up, water is going down. It's all crinkly and bumpy where you have tiny little waves that are rolling around, and then you'll have the huge swells. This combination of very big waves and very small waves, all in different amounts. Like when I listen to the roar of the sea, I can kind of get a sense of like, oh, it's kind of quiet today, or it's really wavy, but I don't know in detail what that mix of waves is. The same is true for light. I can look at this, I can get a sense of the color. Oh, this is whitish. There's about the same amount of kind of light in the reddish, greenish, bluish. That balances out to be something that's pretty white for me. I have like a vague sense of the wavelengths of light that are being emitted. Practically, I really want to be able to split those wavelengths up into more detail. And so the tool that we use for this, whether it is here with old timey tools or with a very fancy spectrograph on a modern telescope, is that we take something that can disperse light on the basis of its wavelength, make a little spectrum for us. So spectrum is the word that we use to talk about a rainbow that gets produced by light being split up into the individual wavelengths that make it up. So when you see a rainbow outside, raindrops are acting as your little spectrograph. When you see light bending through a prism, you're getting to see a rainbow like this. Here I have a little transmission grating that says that this white light here is actually a combination of everything from violet light here through blue and this tealish and greenish and yellowish and orangish and reddish, and then eventually kind of fades away here. All of this light pushed together is what makes up what we perceive as white light. To quantify this, sadly, like during the conference this week, we did not do a lot of like making rainbows and looking like, ooh, what a pretty color in there. But we did look at a lot of spectra. And so the way that we plot these are we so we make a plot that looks like this, where you have wavelength on the x-axis. So this is like shorter wavelengths, tinier waves, and then longer wavelengths over here. And then light flux in watts per meter squared, like per micron of wavelength. So saying like in each little wavelength chunk, how much power is being produced in that little range. And so this right here is the curve that is approximately the spectrum of light that is being produced by this little spectrograph, by this spectrograph here. It is on these spectra. I'm going to show you a lot of these during these talk. I put a little reference up here, which is a little rainbow that corresponds to visible light. So red, orange, yellow, green, blue, indigo, violet. You can make up whatever colors you want along here, but these are the range of wavelengths that correspond to visible light that our eyes are sensitive. If you are to the left of this, shorter wavelengths, that's ultraviolet light. I can feel it when I get a sunburn outside, but I can't detect it with my eyes. If you are to the right of this, if you have wavelengths that are longer than this, then that is infrared light. So that's light that I can still, again, I can't see it, but I can, all of the light that I'm seeing here, that we see here, I can feel as heat. So sometimes I will feel a little bit of warmth coming off of something, and some of that might be infrared light. It's the only way really that I can. Okay, so that just to like give you a little more context on these, because I know I like drew up a curve and neat. What does that mean? So let me take this is just like a little piece of it's just like a little theatrical gel that makes a pretty little color here. And so if I put this in front of my little spectrograph, then it means that this little filter is going to absorb some wavelengths of light. It's going to transmit other wavelengths of light. Let me do that kind of nice magenta one. I think I will also do a little yellow one here. Let me put a blue one on here as well. That should mostly work. Okay, so when I'm sorry about the cough. This is like a flu that I had a month ago. I'm not kidding. So so in here, those colors are like we see them with our eyes, but if we split things up into their individual wavelengths, then you can see that there's detailed absorption happening at very specific wavelengths. So this yellow one is absorbing a lot of the blue and indigo, but letting lots of this other light through. This magenta one, I see a little bit of blue coming through here, a little bit of red, but then most of the green and yellow light is being absorbed by that little filter. And then over here, this blue one, most of the kind of orange and red light is getting absorbed in here, but a lot of the green and blue and violet is passing on through. So I can, in terms of what these look like as spectra, this would be our magenta one. It's like, okay, I have lots of light, but some wavelengths, there's a little bit missing. We would call this an absorption feature. And when we look at some astronomical object where there's light missing at some particular range of wavelengths, due to, in this case, there's this filter that's doing that absorbing. That could be any other, substance. The yellow one on here, let's see, I'll just kind of flip through these. There's blue, yellow, magenta. If I see these, if I absorb different wavelengths, I'll see a different color with my eye, but I'll also be able to measure that via this quantitative spectrum. I kind of make sense to folks. I will also just make the point briefly that these are all, we call these thermal emission spectra. These are light sources that are coming from something being hot. There is a heating element inside of there that gets really, really hot and produces overall the spectrum that we're seeing there. Not all light sources have to be thermal. So if I take my little laser pointer here, if I try to send this through my spectrograph and aim it precisely, okay, so there's a little green light there. And then over on the right, I'm seeing the spectrum of this laser. And the spectrum of this laser is there's only that one very specific wavelength of light. There's not a rainbow that comes out of this because this laser does not emit a range of wavelengths. It only emits this one very, very specific wavelength. Practically what that would look like in terms of a spectrum is absolutely nothing and then a little bit of emission at this one very specific wavelength. And so astronomically, we can kind of have anything. There are lots of different ways that you can be producing light. It can be a combination. I will also highlight a kind of cool point, which is that LEDs, this is an old projector. When the incandescent bulb in it goes, I'm like totally hosed. I can't do this demo anymore. We thankfully use LED lights now, right? That this is a little LED flashlight. The spectrum of this doesn't look like this big, broad thermal emission spectrum with lots of ultraviolet light and infrared light that we can't see with our eyes. Most LED spectra, this is a very cartoonish version, look something more like this. That they're mostly just emitting light at the wavelengths where we actually want to see it. So the reason that an LED light is like 10 times more efficient than an incandescent bulb is that it's not producing light that we don't need anyway. It's really just focusing in on only producing visible light. But everything out there produces thermal emission. This is a source that's kind of like inescapable in the universe. So what that means is this, I have my adorable little old-timey projector here. There is clearly thermal emission that is coming from a very hot light bulb inside of there that is producing a lot of this light. But I will also, let's see. Oh, no. Let me do this in the right order. Here we go. Okay. So, this is a plot where we're going to take some light source, but we're going to change its temperature. So right now, this is what light would look like, something that is 10,000 Kelvin. This is like a hot star. This is like hotter than our sun. That light ends up looking kind of blue because you get a lot of blue light and relatively less yellow and red light. I'm going to change the temperature of this star and make this cooler and cooler. Now at this point, we're kind of talking about planetary temperatures. These are things that are a few hundred Kelvin. That's like 300 Kelvin is approximately the temperature in this room right now. And so as I am changing the temperature, you see that this light never goes away. There's no temperature except absolute zero at which no light is being emitted. But there is, as you go to cooler temperatures, the wavelengths get longer. You move from the visible farther into the infrared. As you get hotter, it gets brighter. That should make sense, right? Like the hotter I make something, the more light it is going to emit. So there's only some temperatures, like things that are kind of a thousand Kelvin or so, where you see any visible light at all. And once you get cooler than that, you stop seeing visible light and things effectively become invisible to you. Most of the stuff in this room right now at about 300 Kelvin is not producing light of its own that I see. I don't see the world glowing bright around me. I mean, like, I do in a sense that I'm kind of curious about everything, but I don't actually see a glow coming off of it. However, if I take a cute little infrared camera that I stole from one of my colleagues, the world does kind of glow. So, for example, our little projector here that I've turned off, is not on anymore, but I can feel that it's still pretty warm, is glowing really, really bright in infrared wavelength. If I step back and look at all of you, don't worry, like, look, probably can't identify you based on what you look like in the infrared. All of you are glowing. All of you amazing humans are warm, and you're producing infrared light that is shining out into the world all around you. You're like your own little planets producing light that we can measure with a camera like this. Let's see, I have all right. Here I took 2 cups, filled one up with hot water, filled one up with snow, and the hot one is hotter, and so it's producing more light. The snow is very, very cold, and so it looks really, really dark in here. They look approximately. It just feels like I'm like working like a steel mill or something. There's like hot magma that's pouring out of it. I feel very impressive when I'm using an infrared camera. Everything is very dramatic. Okay, so let me stop. Great, we'll switch back to visible light. And so on here, like our eyes and our phone cameras are all going to be making measurements at visible light wavelengths. As we go to, but that infrared camera was observing probably closer to 10 microns or so, the wavelengths that were over here, where we were seeing thermal emission. When something is pretty cool, we can still see it here, even if we can't see it glowing invisible. And so when we talk about planets, there is there are kind of 2 kinds of light that we talk about. There's the light that is incoming at us, that is effectively like sunlight that is shining down at us. We call this visible, like becoming shortwave radiation. This is visible light that is coming down from some distant, very, very hot star, and we see that as this short wavelength light. As we look at infrared, though, we're not seeing that light anymore. They're like the visible light isn't contributing anything. Here we are mostly seeing the light that is being emitted by the surfaces around us. So if we go outside, then we see this incoming light from the sun coming down, heating up the surface, and then that warm surface is what's doing this emission that's coming up. You gotta think of light coming down from the sun, but there's also light that is coming up from the planet and trying to escape, head up out of the top of our atmosphere and fly away. And so planets cool to space using thermal infrared light. So like if our planet just continuously kept absorbing sunlight, it would get really hot, right? But we have to have some way to get rid of that energy. And the way that planets get rid of that energy is to emit that energy as infrared light out into. So last night I was walking home. It was cold. I was a little bit of a planet here in that my face was emitting a lot of energy getting out. I could feel it getting colder and colder. My nose got really cold because the wind was blowing on it. Um, uh, every place that I was being warm, like I wasn't cooling as much. I wasn't losing as much energy out to space in there. And so my face was cold because I was losing heat from my face due to infrared radiation that I can see with my infrared camera. Okay, so now towards the end of my talk, we can finally understand this image. When we look at Jupiter, we're seeing, um, uh, when we look at it in infrared light, we're seeing all of these bright spots here are the deeper parts of Jupiter's atmosphere are emitting infrared radiation out into space. And then the darker parts here is just like there's snow and clothes here. That is, those are clouds that are insulating and protecting. You're not seeing emission from the deeper layers at the. So this is why this looks so different with reflected light. In reflected light, sunshine is bouncing, is coming in and bouncing off. Here, you're actually seeing the light that is being emitted by the. Okay, so with our this is great. We have our toolkit now, right? We know that planets exist. We know that they emit light. That light is what we can use to study their atmosphere. So if we precisely measure the infrared brightness of an exoplanet as it passes behind its star, we can learn about its atmosphere. So this finally brings me to how does JWST, James Webb Space Telescope, observe exoplanet thermal emission, the subject of this conference. So the telescope that we've loved for years was the Hubble Space Telescope. It was 2.4-meter diameter. It mostly worked in the UV and visible. The James Webb Space Telescope is enormous. It's 6.5 meters, and it is sensitive to wavelengths all the way out to about 28 microns. That means it can detect the thermal emission from temperatures that are like temperatures in this room. So you can detect the emission that is coming from planets themselves, not these super hot stuff. This is JWST when it was in a lab. You can see some humans down here for scale. It is a very big and very impressive telescope. This is a self-portrait of JWST taken from space. There aren't any pictures that can, or any cameras that can take a picture of this telescope from space, except for itself. So this is what its mirrors look like through some clever techniques. Compared to previous telescopes, JWST is just enormously higher resolution. It's incredibly sensitive. Old telescopes were kind of blurry and tiny. This one allows us to see fainter things and see them. Jupiter with JWST looks incredible. I will say absolutely nothing about this image except that it's gorgeous. But I want to tell you about the observations that we're making of exoplanet atmospheres with JWST, this incredible telescope. So back to our little population plot here. There are planets that we call these hot Jupiters. So things that are the size of Jupiter, they're very close into their star, so they're very hot. And we have them orbiting around a range of stars. So I've highlighted all of the ones on here that are detectable with JWST. If you point JWST at a system, these are ones that you could measure the infrared radiation from the planet itself. And most hot Jupiters that we know of in the universe are detectable with JWST. They're easy planets to study. So one of these is WASP 43b. It's size of Jupiter, pretty hot, around a fairly small star. When JWST pointed at this was part of a large community effort, the Transient Exoplanet Survey, Transient Exoplanet Early Release Science Program. It saw something like this. So there's the brightness of the star as a function of time. There's this big dip when the planet passes in front of its star. But there's also this dip when all right, I'm going to do it again. Sorry. There's the dip when the planet passes in front of its star. But then there's also the dip when the planet disappears behind its star as well. And that's really hard for you to see right now. You're working in visible light, and this planet is pretty dark. But at infrared light, this planet is emitting a lot of light that disappears when it goes behind this star. And so these dips here are the planet disappearing. And so this is a way that you can measure how bright is the planet. You measure how bright the planet is, you know what temperature the planet is. And so we were able to make a map of the temperature of this planet. We actually watched it for the full orbit, so we could see it as a function of longitude. As it orbits around the planet, has a really cool night side, which is extraordinarily hot at about 600 Kelvin, and it has a really hot day side at 1200 Kelvin. So, like by making this map, we can learn how effectively do winds transport energy from the day side of this planet to the night side, just by measuring how bright is it and how hot. There's another planet, WASP 59b. This is another hot Jupiter, where if we JWST observed molecules in this atmosphere. This is another thing that we can do for hot Jupiters. So this is wavelength on the x-axis. This is how bright is it, and these points here are little measurements. And there's a little dip right here at about 4.3 microns, where the planet is a little bit fainter. You agree with me there? There's like this little dip. That dip is a wavelength at which carbon dioxide absorbs strongly. To put this in the context of our little experiment today, remember when we put a filter in front of the spectrum, we got a little dip right there. When you put carbon dioxide in front of this atmosphere, you get a little dip at this wavelength range that corresponds to carbon dioxide. You get an absorption feature that comes from a filter over your planet. Is its carbon dioxide atmosphere absorbing that light? Light. Yeah. So this is cool. This allows us to measure the compositions of atmosphere. Right? Like you do this for lots of different molecules. You can piece together what molecules make up a planet's atmosphere. That is like the closest thing that we get knowing what Earth's atmosphere is made of, is measuring the molecular composition. All right. We're going to say, so for hot Jupiters, JWST is measuring dynamics and compositions, all of this really, really cool stuff. You'll find news stories about it over the years to come. Or rocky planets, things that are super tiny, things that are the size of the Earth. They're hard to study. I'm highlighting the ones on here where it's like vaguely plausible to be able to detect air thermal emission with JWST. You see fewer planets on here. They're tiny little planets. They're hard to study. And you'll notice that a lot of those planets are around really small stars. The reason for that is if we're looking for a planet disappearing behind its star, compared to the horrifyingly bright giant light bulb here, you have a tiny little red star that is, maybe 1/5 or 1/10 the size. A planet disappearing behind that is going to be a lot easier to detect. Smaller stars are easier to see. They also turn out to be like really complicated. They have these like nasty magnetic fields and high energy radiation coming off them. These are stars that are very, very different from the sun. And it's an open question of like, can a planet around one of these tiny stars retain an atmosphere? We just don't know. We'd love if they can, so that we can study them, but it might not be possible. And so this question of can rocky planets around small stars have atmospheres is one that JWST is working on answering right now. And the way that we do this is kind of cool. This is if you think about energy that comes in from its star and heats the surface of a planet, that energy has to radiate away into space. If you're standing on the moon with no atmosphere, that energy comes in and has to radiate away right away. And so you won't get any energy going around to like the other side of the planet. There'll be a dark part that you don't see. If you have an atmosphere, on the other hand, that atmosphere could circulate some of that energy around to the other side of the planet. And so what you see coming off of the day side of the planet would be a little bit cooler because some of that heat is going to the other side and radiating away from there. So if we look at, say, the moon and Earth in our own solar system, the moon has a really hot day side and its night side is really cold. It is not being illuminated. Whereas Earth has an atmosphere, it's also rotating really rapidly, which helps a lot as well. And so the temperature of Earth is pretty consistent across the whole sphere of the Earth. That means the moon looks really hot if you look at it in infrared radiation. The Earth looks relatively cool because it's emitting over a much larger area. So we're starting to make measurements of these. One of my favorite planets is LTT 1445AB. Student Pat Wachiropan analyzed these data from JWST. Rocky planet that receives about the same amount of energy that Mercury receives from its sun, but it's just bigger. So like if you made Mercury bigger, could it retain an atmosphere around one of these stars? And Pat's conclusion is, it doesn't seem like it has a thick atmosphere. It could still have a thin one, but it definitely doesn't have a like thick Venus-like atmosphere, which is one of the hypotheses that we were. Okay. And thankfully, the JWST is devoting about 500 hours of director's discretionary time to follow up and observe many planets to try to figure out which ones have atmosphere. Don't know yet, but hopefully in a few years we will. Okay, in my -2 minutes, I do want to emphasize the point that I have sneakily through this talk by talking about exoplanets brought up giving you all the tools that we need to think about an important phenomenon here on Earth, greenhouse effect. Right? That the greenhouse effect is important for Earth's climate, where energy from the sun travels clearly through Earth's atmosphere, it's absorbed by the surface, and the surface warms up. And then the surface tries to re-radiate that energy out into space, and the atmosphere stops. Seeing this kind of quantitatively on here, I have a plot down here that this is how much do water and carbon dioxide absorb light as a function of wavelength. Now, all of these gases are pretty clear visible light. That means that like light can come down from the sun and make it down to the surface. But water and carbon dioxide in particular are very opaque at infrared wavelengths. They block a lot of light. That means this energy that is coming from Earth's surface and trying to radiate up, out, away into space, it's absorbed by the atmosphere that is full of water and carbon dioxide. The more of these molecules that we have in the atmosphere, the more our atmosphere is going to absorb, the more that we are going to slow down that escape of radiation out into space. So the one other place where we can see this is in an actual greenhouse, which has been steadily warming up right here. So you've had a star that is making visible light, putting it in through the glass of this little greenhouse here, and warming up the plants on the inside. This glass, kind of like water and carbon dioxide, it's good at transmitting visible light. It's bad at transmitting infrared light. It absorbs all of it that gets trapped inside of it. All right, take the lid off. There is, you can see the warm glow on the inside of this terrarium, that those little, like all of the little plants in there are glowing, trying to escape, trying to let their infrared radiation escape to space. But the greenhouse is trapping it. Oh, I should really pause because I want to hear all of your amazing questions. And so I will leave you just with 3 thoughts. One of these is that the sky out there is full of exoplanets, thing you should know. JWST, this incredible telescope, is observing their atmospheres. Maybe more than anything else is just that light is power. When you go outside and feel the sun shining and hitting your face, you are absorbing power that comes from the star. You have the choice to do whatever you want with that power. I personally, astronomers, I think really like to use that power in our way to be curious and learn, and try to help teach the world about all of the cool things that we're discovering. And I hope and I know that many of you are doing your own thing. So I will leave it there, and take any questions.
2 questions. One is the Doppler effect at all useful in determining like rotational velocity, or is that too small an effect? Second question is, would we be able to see evidence for exoplanet moons yet? And if so, how?
Yeah, so the first question is the Doppler effect important for studying these planets? Yes, it's the main way that we measure the mass of a planet. I didn't talk about that at all, but that's mainly how you measure a mass. And then the other question is there evidence for exomoons yet? So moons around any of these other objects? I would say no. There have been some tentative claims, but people have been really cautious because this would be a really cool thing, and lots of people would love to find a moon around one of these exoplanets. But people, the folks who have been working on this have done these very careful statistical analyses that ultimately end up with like, well, it's not like it's not absolutely a guarantee that these exist. So I would say not strong evidence.
Well, I thought I must be totally wrong because I thought what you were studying atmospheres was by measuring the absorption spectrum as the planet transited in front of the star and its light shone through the ring of atmosphere around the planet instead of the emission spectrum from the planet. Was I wrong, or is that another way that you can study atmosphere?
Yes. So the question was, isn't it possible to study atmospheres in a totally different way for exoplanets? In particular, when the planet is passing in front of its star, see how that starlight gets absorbed by the planet's atmosphere, rather than the planet emitting light itself. And yes, that is exactly another method that we are using, that we could have had equally as fascinating of a conversation about that method as well. This particular conference has been focused more on the thermal emission side. And so I really just want to focus on this one area in this talk. But yes, that is another fascinating method that we can use. And it's really cool if you can apply multiple methods to the same planet to learn about it in a more 3D. Yeah, right here.
You guys mentioned before that CO2 absorbs at a certain wavelength. Do we have like a cohesive list of what gases absorb at what wavelengths, and are there multiple gases that absorb it the same? Like, can you say conclusively that it's CO2, or is there other things that absorb at the same wavelength and it makes it confusing, or no?
Yeah, great question. So the question here is there a comprehensive list of wavelengths at which each molecule absorbs? And do you ever run into a problem that you see, say, an absorption feature, but you can't tell which molecule it is? Yeah, so yes, we have pretty good databases of atomic and molecular line lists. They are not perfect, and that is still an active area active area of research for many lines that we are still trying to figure out. Part of this massive collaborative effort of thousands of people all around the world is trying to understand planetary atmospheres better. And that is one that matters both for us as exoplanet scientists and particularly to Earth scientists as well, in Earth's atmosphere. And so, yes, if you had, let's see, if you had only one very specific wavelength range, then often it can be very confusing. What is causing the bump that I am seeing in here? And there are many times where there could be overlaps. It can be hard to figure out. And so one of the things that we really love about JWST as a telescope is that it allows us to observe from like basically down to the visible all the way out to this far range here. And so getting a wider wavelength range is really helpful for kind of unambiguously identifying which molecule. Yeah. And the Melly.
So when you have an exoplanet on the target star, you're measuring, and it goes in front of the star and you're measuring energy. The dip is the loss of energy from the star, the visible light. When it goes behind, what you're measuring is the loss of red light in exoplanets?
Yes, exactly.
Okay,
Yes, thank you. Yes, I'm going to reiterate that again. So the question was, when the planet passes in front of its star, here, I won't do it with the horrible thing. We'll pretend this is my star. When the planet passes in front of the star, you're seeing the dip that is caused by the planet blocking some of the star's light from being. And then as the planet goes behind the star, you lose the planet's light. If you were observing at visible light wavelengths, so say here's a pretty good. So if you're observing at visible light wavelengths, then you're not going to see any light from the planet. The planet is so faint that it contributes virtually nothing to the light of the system. But if you're observing at these long wavelengths, like with my handy little IR camera, then this planet is glowing much more appreciably relative to the brightness of the star. And so when the planet disappears behind its star, you get to see this, albeit still very tiny dip of the planet disappear. And so there, between these two methods, we can piece together a kind of.
So the light from the star can dip. Can it like go up ever?
Ooh,
Possible?
so the light from the star can dip, but can it go up? Can it ever get brighter? Yes, there are multiple ways that this can happen. So one, the star itself can flare. So like complicated magnetic fields of a star can rearrange you, the sudden burst of energy that your star, which seems pretty constant, instead of going down because of a dip, you get this like big burst of energy that comes out and it looks a lot brighter for a little while and that decays away. There's another really cool way that that a star can get brighter, is in some very specific circumstances, if you have a very massive object passing in front of it. So this might not even be a planet, maybe it's a white dwarf or a black hole or something. The gravity from that object and gravitationally make a magnifying glass that magnifies the light of the background star, and therefore makes the star look a little bit clear. Like a weird thing that's been seen only a couple of times, but it's really, really cool. Okay, I think Ed told me I should cut things off, but I'm happy to stick around for a while and answer any more questions.